Okay, now we want to talk about the curvatures of space and time. And I want you to think about, what did you learn in your ordinary geometry course, either in high school or in college? Uh, Remember that you did it on a flat sheet of paper, and this was called Euclidean geometry. And so one of the things that you should remember is that if you have a triangle is going to have three angles, and then it always turns out that in Euclidean geometry, when you add together these three angles, it always has to be 180 degrees. Okay, another thing that you should have learned is that the circumference of a circle, C, is going to be equal to 2 pi r, where r is going to be the radius of the circle. So the circumference is the distance when you go all the way around. And then another thing that you should have learned is that if you've got two parallel lines on a flat piece of paper, they never intersect. So they just continue forever and ever parallel to each other. So what's the big deal? Well, it turns out that there are other kinds of geometry that you could learn in college. And so those would be non-Euclidean geometry. And so one type is going to be spherical geometry. And so you can try this if you want. You need a basketball. So if you've got a basketball with a marker or something, make a triangle on that basketball and then measure the angles inside that triangle, and it turns out it is not equal to 180 degrees. Okay, make a circle on your basketball and then measure the circumference of that circle and then measure the radius of that circle, and then you're going to find out that the two don't match, that the circumference of the circle is not equal to 2 pi times the radius. And then make two lines on that circle, and you're going to find that those two lines will eventually hit each other. So that on a spherical surface, the laws of geometry as we know them, they don't work. And then there is yet another kind of geometry that's hyperbolic. So you have hyperbolic geometry. And again, the sum of the angles is not going to equal 180 degrees. The circumference of a circle on a saddle is not going to be equal to 2 pi r. And then two lines that start out being parallel to each other are, again, not going to remain parallel. They're going to do something else. Now, that was for Euclidean geometry that uses 3 dimensions, so x, y, and z. So you can add an extra dimension to it so that you can have, we can talk about space and time in a flat, on a flat sheet of paper, in spherical geometry, and then in hyperbolic geometry. So you can learn all about this if you want. You can read about it on the internet. You can actually take a course on it and learn all the different formulas that goes with it. So what are then the different types of universes, and how are they related to the critical density of the universe, and then how are they related to what is the universe going to do? So the first one is, if the overall density of the universe is greater than the critical density, so that means that there is too much mass and energy in the universe. Mass and energy cause gravity. So if there's too much mass and energy in the universe, then the expansion is eventually going to stop, and then the universe is going to collapse. So we're going to call this a recollapsing universe. and the curvature of space and time is going to be spherical, and the universe is going to collapse. If, however, the universe has exactly the right amount of mass and energy, so the mass and energy density of the universe is actually equal to the critical mass and mass energy density, then the universe is a critical universe. The curvature of the universe is going to be flat, and the universe is eventually going to come to a stop, but it's going to take an infinite amount of time for that to happen. So think about trillions and trillions and trillions of years into the future. We'll go to infinity and beyond. All right? So it's going to take an infinite amount of time for the universe to come to a stop, but it eventually would. All right, then the next thing is, what about if there is not enough mass and energy in the universe? So then the mass energy density of the universe is going to be less than the critical amount necessary, and then we have what's referred to as a coasting universe. The curvature of the universe is going to be hyperbolic, and the universe is going to expand forever at a constant rate. So the expansion of the universe is going to be a constant. But if there really isn't enough mass and energy in the universe, then it's going to be less than much less than the critical mass energy density. Then we have an accelerating universe, and then the curvature really could either be spherical, flat, or hyperbolic, and then the universe is going to expand forever at an ever-increasing rate. And that's what Hubble's law is showing us. So if you recall, Hubble's law showed that the galaxies are moving away from us, and the further away they are, the faster that they're moving. So the universe, we think, is really expanding at an ever faster rate. Okay, now another way of thinking about this is with a pen and thinking in terms of orbits. So if you recall, back in unit number 1, we talked about the orbits of different kinds of objects, and we found that they could either be an elliptical orbit, or they could be a parabolic orbit, or they could be a hyperbolic orbit. And it all came down to the overall energy of the particle. So a particle has both kinetic energy, so energy kinetic, and then it also is going to have energy gravitational. So this is the potential energy, this is the kinetic energy, and when you add the two together, you get the total energy of an object. Could be a rocket, it could be a planet. Now this is trying to make the rocket crash. So this is gravity, it's pulling everything in. This is the kinetic energy, it's trying to make the rocket ship or the planet escape, to go outwards. So notice how similar this is to general relativity, where you had this term over here was related to gravity, and then this term over here was the one that had the cosmological constant, and then this was the dark energy. So this was making the universe collapse, this was making the universe expand. And so depending on which of these two terms was winning, was gravity winning or was kinetic energy winning, you had a different kind of orbit. So that, for example, if gravity was winning, the rocket ship could not escape, and then it would have an elliptical orbit around whatever was causing the gravity. If, on the other hand, the rocket ship had exactly the right amount of energy, and energy equal to 0, meaning these two terms were balanced, then it would escape, and it had the parabolic orbit. If, on the other hand, the rocket ship had more speed, more kinetic energy than gravity, then it would really escape, and it had the hyperbolic orbit. And so also notice that a sphere is a special case of an ellipsoid. It's the same way that the circle is a special case of the ellipse. And then notice that you still have that hyperbolic curvature in space-time versus hyperbolic curvature in 2 dimensions. So I know this. I'm just enjoying this. So I'm sorry. This is just such cool stuff. So with relativity, we're talking about 4-dimensional space-time and curvatures in it, whereas when we were talking about planets, it was more 2-dimensional, and we were talking about the different kinds of orbits that they could have. So mathematics and physics, it's really good stuff that you can take stuff that you've learned from this particular area and carry it over to this area over here. All right, so let's talk about the future of the universe in our next segment.